Jupiter is not what most people think. For decades, textbooks have called it a gas giant, a massive ball of hydrogen and helium floating in space. That's partly true, its upper atmosphere is mostly gas. But beneath those iconic clouds, the planet behaves in ways that almost defy imagination. Jupiter is not just a balloon of gas. Deep inside, hydrogen is compressed into liquid and even metallic states under pressures millions of times stronger than Earth's atmosphere. So while it's made of gas, most of the planet isn't gas in the way you usually imagine it. The first close-up images came from Pioneer 11 in 1974, revealing the banded clouds and enormous storms. Voyager 1's 1979 approach added motion, showing storms bigger than Earth and that familiar great red spot swirling for centuries. The footage was breathtaking, but it only scratched the surface. Scale is where Jupiter truly boggles the mind. Over 1,300 Earths could fit inside it, and it outweighs all other planets in the solar system combined. If Earth were a grape, Jupiter would be a basketball next to it, a visual most of us can barely comprehend. So how did it form? The dominant theory, core accretion, suggests Jupiter started as a solid core of rock and ice in the early solar system. As this core grew, its gravity pulled in enormous amounts of hydrogen and helium from the protoplanetary disk, eventually forming the giant we know today. Some researchers debate whether parts of Jupiter's formation involved gravitational instability, where dense regions in the disk collapsed directly, supplementing core growth. Either way, Jupiter's interior is not uniform. If it were a simple solid core covered by gas, we wouldn't see the mysteries revealed in the 1990s. That's when an extraordinary event occurred: the Shoemaker-Levy 9 comet impact in 1994-1995. Fragments the size of mountains slammed into Jupiter at over 60 kilometers per second, creating scars visible from Earth. This collision gave scientists an unprecedented glimpse into the planet's deeper layers. Combined with data from Galileo, which orbited Jupiter and even sent a probe into its atmosphere, we started learning that beneath the clouds lies a world dominated by superheated liquid hydrogen, eventually transitioning into metallic hydrogen, generating Jupiter's magnetic field. And that's just the beginning, because once you descend below the clouds, the physics of Jupiter becomes almost alien. The ocean beneath the clouds, hotter than lava, deeper than any ocean on Earth. The cosmic collision that exposed Jupiter's secrets in the summer of 1994, Jupiter faced one of the rarest cosmic events in human history. A comet, Shoemaker-Levy 9, had been captured by Jupiter's immense gravity. But instead of remaining intact, the comet was torn into more than 20 fragments, each kilometers wide, stretched across space like a cosmic necklace. Then the fragments began their fatal plunge. They slammed into Jupiter at speeds exceeding 60 kilometers per second, over 216,000 kilometers per hour. The impacts were cataclysmic. Some explosions unleashed energy equivalent to hundreds of millions of atomic bombs. Dark scars, larger than Earth itself, appeared in the planet's atmosphere. Plumes of debris shot thousands of kilometers into the sky, lingering for months. From Earth, telescopes like Hubble's Space Telescope captured the aftermath, revealing Jupiter's atmosphere like a canvas etched with fire and shadow. Yet the true revelation came from a spacecraft already in the neighborhood. Galileo had been orbiting Jupiter, gathering data on the planet and its moons. By incredible coincidence, it arrived just in time to observe the comet fragments striking the far side of Jupiter, giving scientists a front-row view of material from deep beneath the clouds. What Galileo found challenged assumptions. Water, enormous quantities, had been lifted from the lower atmosphere into the upper layers by the impacts. This water didn't just exist in the clouds. It hinted at a dynamic interior where heavy elements mix with hydrogen under extreme pressures and temperatures. The impacts also gave clues about Jupiter's storms and magnetic behavior. The violent collisions stirred the atmosphere, sending shockwaves through the planet's massive weather systems. Lightning storms became even more intense, and deep convective currents pushed the clouds into temporary chaos. But the most fascinating question remained: what lies beneath? Galileo's instruments suggested a layered but dynamic interior, far more complex than the simple gas giant model. Hydrogen, compressed under crushing gravity, transitions from gas to liquid and eventually into metallic hydrogen, a state that conducts electricity and powers Jupiter's immense magnetic field. This collision, combined with precise gravity measurements from Galileo, marked the first real glimpse into Jupiter's hidden depths. For the first time, we began to understand that the planet's interior isn't just gas and clouds. It's a superheated, superpressurized metallic ocean stretching thousands of kilometers below the surface. And this was only the beginning. Because these discoveries set the stage for NASA's next mission, Juno, launched in 2011, designed to probe Jupiter's core and magnetic field with unparalleled precision. By the end of the next decade, scientists would be rewriting everything they thought they knew about the largest planet in our solar system. Descending into Jupiter's hidden ocean hotter than lava, deeper than any ocean on Earth, and unlike anything we can imagine. The ocean beneath Jupiter's clouds from a distance, Jupiter looks serene. Bands of clouds swirl, storms rage in slow motion, and the great red spot spins like a centuries-old hurricane. But appearances deceive. Those colorful cloud tops, mesmerizing as they are surprisingly thin, only about 50 kilometers thick. Below this veneer, pressure rises dramatically, creating conditions no human could survive. And as gravity compresses the layers beneath, hydrogen, the lightest element in the universe, begins to behave in ways that defy everyday experience. Around 1,000 kilometers below the clouds, the familiar hydrogen gas transitions into a dense liquid. There is no solid surface, no ground, only a vast ocean of liquid hydrogen, hotter than lava and deeper than any ocean on Earth. Unlike Earth's water oceans, this is a superheated, high-pressure environment, a world where chemistry and physics are pushed to extremes. The deeper you go, the stranger it gets. As pressures climb to millions of times Earth's surface pressure, temperatures soar to thousands of degrees Celsius. Hydrogen enters a state called metallic hydrogen. What does that mean? It remains liquid, not solid, but the electrons are stripped from hydrogen atoms, flowing freely like electrical currents. This exotic metallic ocean generates Jupiter's enormous magnetic field, the strongest of any planet in our solar system. Essentially, Jupiter's core is a magnetic dynamo, powered by an ocean of liquid metal. This layer stretches tens of thousands of kilometers deep, making it the largest ocean of any kind in the solar system. And even beneath this metallic ocean lies the planet's core, but it's not solid or clearly defined. Data from Juno suggest a fuzzy mixture of rock, metal, and liquid hydrogen. The boundary between metallic hydrogen and heavier elements is blurred, like a thick planetary soup stirred by gravity. So to summarize, the clouds we see are just a thin atmospheric skin. Beneath them lies an enormous ocean of liquid hydrogen, superheated under crushing pressure. Deeper still, hydrogen becomes metallic, conducting electricity and powering Jupiter's magnetic field. At the center, there is no simple solid core, only a diffuse, dynamic mix of elements. Jupiter is not just a gas giant. It is a planet of extremes: heat, pressure, magnetism, and gravity combine to create a world unlike anything on Earth. And here's the cinematic kicker. Every time we think we understand Jupiter, new data surprises us. The planet continues to defy expectations, reminding us that the solar system is stranger than textbooks suggest. The core of Jupiter, solid, shattered, or something far stranger than we imagined. Jupiter's core, solid, shattered, or a planetary soup. For decades, scientists assumed Jupiter's interior followed a neat structure. Clouds on top, liquid hydrogen beneath, metallic hydrogen further down, and at the center, a dense, solid core made of rock and metal, roughly the size of Earth. Logical, clean, predictable. But reality is far more complex. Data from Juno, combined with gravitational measurements, revealed a surprising truth. Jupiter's core isn't a compact, solid ball. Instead, it appears fuzzy, a diffuse mix of rock, metal, and liquid hydrogen, blending seamlessly into the metallic hydrogen ocean above. Think less marble, more stirred planetary soup. How could such a structure form? One idea involves cataclysmic collisions during the early solar system. A massive protoplanet, perhaps 10 times Earth's mass, may have slammed into young Jupiter. The energy could have disrupted the original core, scattering material upward into the surrounding metallic hydrogen layers. Simulations on supercomputers show this could create a temporary fuzzy core, but over billions of years, heavy elements should settle into a compact center. Yet Jupiter's core remains diffuse. This suggests either unusual formation conditions or an ongoing internal process we don't fully understand. The fuzzy core also helps explain Jupiter's massive size. With material distributed across the interior rather than locked into a solid center, gravity could pull in gas more efficiently, allowing the planet to grow into the enormous world we see today. So Jupiter isn't just big, it's alien. A planet where matter exists in extreme states, layers of hydrogen flow like liquid metal, storms rage thousands of kilometers deep, and the very core defies simple classification. And this is why astronomers are fascinated. Jupiter challenges every textbook assumption about giant planet formation, forcing us to rethink what gas giant really means. Why Jupiter is not just a planet but a cosmic guardian, and how it almost became a second sun. Jupiter, guardian and almost star. Jupiter is more than a planet. It's a gravitational titan, a magnetic powerhouse, a cosmic shield. Its enormous gravity captures or deflects comets and asteroids that might otherwise threaten the inner solar system, Earth included. Yet Jupiter's influence isn't purely protective. Its gravity also redirects space debris, shaping the early solar system and potentially sending objects toward Earth, contributing to both destruction and opportunity for life to evolve. And here's a mind-blowing what if? If Jupiter were about 80 times more massive, nuclear fusion could ignite in its core. It wouldn't be a planet, it would be a second sun. Two suns in the sky, two centers of gravity, an entirely different solar system. Instead, Jupiter exists in this delicate middle ground, too massive to be ordinary, yet not massive enough to ignite. A failed star, a metallic ocean world, a planet where the core is blurred and storms dwarf continents. Even after decades of missions, from Pioneer 11 to Voyager 1, Galileo, and Juno, we are only beginning to grasp the truth. Every discovery makes Jupiter stranger, more extreme, and more fascinating. Its liquid metallic hydrogen, fuzzy core, and magnetic field remind us that the solar system is far weirder than we imagined. If the largest planet in our solar system still surprises scientists today, what secrets await in the exoplanets orbiting distant stars? If you want to explore more cosmic mysteries, make sure to hit that like button, share this journey, and subscribe so you don't miss the next revelation. The universe is waiting. Are you ready to see it?